For number 1, we'll be using the change of base theorem to find the logarithm. And the change of base theorem is on page 454. And logarithms are very difficult to calculate by hand. And so we like to use a calculator, but most calculators only have a couple of bases programmed in. So either log base 10 or log base e, which is called the natural log and abbreviated ln. And so when we use the change of base rule, that lets us get to one of these common logarithms, and then we can use our calculator. So log base 2 of 6, we're asking what exponent should 2 be raised to in order to get the result of 6. And that's hard to find out by hand, but with the change of base theorem, we can do it easily on our calculator. So what we do is either log base 10 or log base e. I'll use log base e, the natural log. And so we do log base e of 6 on top and log base e of 2 on bottom. And just on your calculator, type in ln6 and then hit divide by and then type in ln2. And when you hit enter, you'll get your result. And don't round along the way. Don't round to 4 decimal places until you reach the very end. But that is your solution. And just to check the solution, I used the calculator here on Google. I raised 2 to that exponent we calculated. And because we rounded, it's not exactly 6, but it's an answer very, very close to 6. So we found log base 2 is 6, and it tells us the exponent needed to put on 2 in order to get an answer of 6. For number 2, we're looking at a radioactive substance that's decaying. And we have a formula here for the amount of the substance that's left after a given amount of time has passed. And the time will be measured in years. And so to use this formula, we're going to need to use the number E. So whenever you see an E in mathematics, it stands for a specific number. And we have to use a letter to stand for that number, because the decimal never ends. It's an infinite decimal that goes on and on and on forever. So a short abbreviated version, E is right around 2.71828. So whenever you see E, think of this value. But just know, and I'm here on the Wikipedia page, just know that the decimal for E never stops. So here it's written out a little bit further. And I think it says 50 decimals here. And I'm sure on the internet you can find it written out to 1,000 decimals or 100,000. But this decimal does not end. So we have to use the letter E to represent this number. And so we're going to use our calculator to work with this function here. And your calculator has the value of E stored to lots and lots of decimals already built into it. So it's helpful to use the E key rather than trying to type in the number E. It just saves time, and it'll be more accurate if you use the E key. So find the E key on your calculator, plug a 40 into the function. And so it goes up here in the exponent. Reduce that exponent by multiplying those values. And now on your calculator, type E raised to that exponent. And you get a result. Multiply by 250, and you have your final answer. And we're rounding to the nearest whole grams, so this rounds up to 70 grams. For number 3, we're dealing with a compound interest problem. Compound interest is talked about on page 426. Here's the formula you'll see. And so you need to identify what all the different letters in the formula, what values they're taking on. So this much is invested. That is our principal. P stands for principal. It's invested for 12 years. That would be in there for our T. Time is measured in years, so 12 years. It's at 4%. So our interest rate is 0.04. So convert that to a decimal. It's 0.04 is 4%. And it's compounded quarterly. Quarterly is 4 times per year. And that's what N stands for, the number of times per year that we're compounding the interest. And A stands for the amount of money in the account. So A is the amount. But that's what we're solving for. We're trying to figure out what A is, so we just need to plug all these values in to the formula. So plug them all in. and then start doing some reducing. So 12 times 4, the exponent is 48, and 0.04 divided by 4, you get 0.01. And I reduce further inside the parentheses by actually adding those numbers together. And now I can take that value and raise it to the 48th power. And you get a result here, and multiply that result by 1972. And you get your answer here, and it's the amount of money that will be in the account after 12 years has passed.